questions in the form of a question. Our revision will also be done. See, wavelength is given to you 6000 angstrom. Small d is given 10 millimeters. Capital D is 5 meters. Capital D is what? It's the separation between the slits and the screen. This separation is capital D. And small d is what? Small d is the separation between both the slits. That is 10 millimeters. So now you have to do what? You have to calculate linear separation of second bright fringe from central maxima. If central maxima is, let's say, formed here, somewhere here, you're getting central maxima. And this is the second bright fringe that you're getting. So this separation yn, remember yn we had calculated for the bright fringes as well as for the dark fringes. So right now we have to find it for the bright fringe. So C class, n lambda capital D by small d was the formula. For bright fringes, linear separation from the central maxima, this is n lambda capital D by small d. So n is given to you 2. So that will be 2 lambda capital D by small d. And this is the value of y2. Now put in the values of y2. Y2 will be 2 into wavelength is given 6,000 angstrom. No. So we can write it as 6 into 10 to the power minus 7 meters. Right? And capital D separation is 5 meters. And small d was given 10 millimeters, the separation between the both the slits. So 10 millimeters makes it 10 to the power minus 2. 10 into 10 to the power minus 2, so 10 to the power minus 2. So if you solve this, you will get it 6 into 10 to the power minus 4. This much meters is the separation of the second bright fringe. Suppose this one is the central maxima. So this is your second bright fringe. From here you have the separation. This separation, this linear separation, this is known as by n. Second question says same thing you have to calculate it for the dark fringe. So this formula we had revised it for the bright fringe. Now same type of formula we did for bright fringe, dark fringe as well. But just the difference was that 2n minus 1 by 2 also remained apart from this entire term. Now n is 2. So that will be 2 into 2 minus 1. This is 2n minus 1 into lambda. Wavelength is again 6 into 10 to the power minus 7. Capital D is 5. 2 and small d is 10 to the power minus 2. So 4 minus 1, 3. 3 lambda d by d you're solving. No, second we have to calculate a third one. Linear separation of second only, no? We have to calculate, fine. So if we have 4, this becomes 3. So 3 into 6. This is 6 into 10 to the power minus 7 into 5 by 2 into 10 to the power minus 2. This much meters, whatever you get your answer. Third part says fringe width. So fringe width also we had done. Fringe width's derivation can also come in your exam. Fringe width was beta. Lambda capital D by small d. This is beta. So lambda's value is 6 into 10 to the power minus 7. Capital D is 5. Small d is 10 to the power minus 2. So 30 into 10 to the power minus 5. Or you can write it as 3 into 10 to the power minus 4 meters. This is fringe width. So formula of fringe width was lambda capital D by small d. Last thing, angular fringe width. Angular fringe width we had done, which was lambda by small d. So lambda can again be written as lambda is wavelength, small d is separation between the slits. So 6 into 10 to the power minus 7 by 10 to the power minus 2. That will be 6 into 10 to the power minus 5 radian. Fifth part says, okay, fifth part we do not have. Suppose, let's say, we only have 4 parts, no? But suppose, let's say, you have Instead of, let's say, some refractive index, some medium has refractive index as 2, and you're shifting. So this was fringe width in air. So fringe width in that particular medium will be fringe width in air divided by the refractive index. So you got here as 3 into 10 to the power minus 4 divided by the refractive index will be 2. That is 1.5 into 10 to the power minus 4 meters, because this is the width of the fringe. So this was what we had studied in the last class, as well as a numerical from this topic. One small topic is there, sustained interference and interference with white light. These topics are left. Note down this question, the solution. Any doubts you have from the last class, you can ask me. This is given in the question. That second bright fringe, number of bright fringes mentioned to you. So that is a part from given from the question only. And in fifth part also, this I have taken randomly. Suppose this is true. It could be any number. Yes, I'll scroll. Yes, if it would have been given first, then N you would have taken as 1. Yes, class. So I hope you all have written it till here. See, one very small topic is sustained interference. From sustained interference, you can get theory questions. Theoretical question will only come from here, but very less chances are there that questions from sustained interference come. So at the end, revise it. See, sustained interference means what? Intensities are not changing. Like whatever bright and dark fringes are formed, with whatever intensities they are formed, they are not changing. All right, whatever intensity, let's say very bright fringe is formed. So intensity of that very bright fringe, that won't change. This is not, sustained interference is not the last topic of this chapter. You have some more portions from interference left, then complete diffraction is left. 3 topics I told you, no? So this is not the last. So in sustained interference, whatever bright and dark fringes are formed, their intensities is very high. So if the intensities is high, they look very in good contrast with each other. Like the bright and dark, you'll be able to distinguish them in sustained. But there are certain conditions. 4 conditions are there. Just remember these 4 conditions, because if a question comes from sustained interference, then directly the definition along with these 4 conditions will be asked. So first is sources should be coherent. So what did we discuss regarding this coherent sources? Coherent sources are those sources that emit the wavelength and light frequency of the this Sayyida Rufia, your mic is on, please. Okay. So four conditions are there. So coherent sources are sources that have that emit waves which have the same wavelength and frequency. So and with a constant phase difference. So the sustained interference is only possible by the sources that are coherent, monochromatic, means emitting light of single light. Slit width should be maximum, means the small d separation no between both the slits that we take. This separation between the slits. This separation should be greater. Fine, this separation should be greater. And the separation between the double slit and the screen means capital D also should be large. So both capital D and small d both should be large. Then only sustained interference is possible. So it's a small topic, very small topic. If question comes, write down everything from here. Note it down. One more small topic is like this, that is interference from white light. That I'll tell you. First, note it down. No. See, coherent sources are sources. When we say coherent sources means such two sources that emit waves and both the waves are having the same frequency. Let's say 10 to the power 5 hertz. So both the waves will have 10 to the power 5 hertz. 11 meters wavelength, so 11 meters wavelength. And phase difference between them remains constant. If suppose, let's say they are having a phase difference of pi by 2. So throughout their superimposition, they will be having the phase difference pi by 2. So those sources are known as coherent sources. All right, class. Now, see, you have one topic known as interference with white light. White light, you already know when we were doing prism, that time also we discussed that if a white light is passed through a dispersive medium, then once the light passes through the dispersive medium, it gets spread or split into all of its 7 colors. So, same thing will happen here also. If you are interfering it with proper white light, then what will happen? According to their wavelength, all the 7 colors will spread. This is not just red and blue. This is depicting you all the 7 colors here also and here also. All the 7 colors are present. What will happen at the center? See, here I think I've written also. Yes. On using white light, central bright would be white, next fringe would be violet. After few fringes, pattern disappear due to overlapping. Means this one is white. Now you will get it according to the rainbow colors that you have. It is according to this pattern, Web cure. And same way here also, it will happen the same. Web gear and complete tilted. And because we know in interference, only in sustained interference, intensities remain fixed. Right now, intensities do not remain fixed. So what will happen? Here, it will keep on disappearing. Slowly and slowly, it will disappear like this. The intensity will lower, and because of overlapping, it will disappear. Note it down. Then one very important topic that you have is intensity distribution curve for interference, because you'll be getting the same curve for diffraction, and in the exam you can be asked to compare them. So note it down. Then we'll do one very important topic, intensity distribution curve. All right, class. Now see. Okay. Now, yes, intensity distribution curve is very important, class, from both. If whether you have your diffraction or you have interference. Now, see, for identical coherent, so okay, I'll wait for 2 more minutes. Okay. Yes, no, that is not necessary for white light. It can be formed because of any light. That is not necessary. We are just studying the specific case if it is for the white light. Now, see, if you have intensity distribution curve for identical sources, see the formula for intensity for the bright fringes. The formula is under root I1 plus under root I2 whole square. Now see here I1 is equal to I2. So if you put it I1 as equal to I2, you get 2 under root I1 whole square, and that becomes equal to 4 times I1. Now see here you are getting 4I1. If you are having this in terms of dark fringes, your intensity will be under root I1 minus under root I2, this whole square. So now when you say I1 is equal to I2, these will get cancelled and you will get it as 0. And if you have, suppose, non-coherent sources, Now see, for non-coherent sources, I1 plus I2 plus 2 under root I1, I2 cos phi. Now this intensity is variable. So see, when you plot the graph, for this coherent sources, you are getting it maximum at 4i. For non-coherent, this is independent of phase difference phi. So this is 4i and this is the non-coherent source one. Plotted based upon this only you have it. plotted this graph?
Done, ma'am.
Yes, class answers. Not 5, just once again try. C class for this question, no, not 5 or 6. That way you don't have to do. Two more minutes I had already given. Let's just discuss it now. See, it says that in a beam of light consisting of two wavelengths, 800 nanometer is there and 600 nanometer is there. For just differentiation, I have taken one as blue and one as red in the figure. Figure also will not be mentioned to you in the exam. This you have to draw on your own. It says that at a particular point, this separation from one of the fringes is ym and other fringes is yn, and both of them overlap with each other. So screen distance will remain the same. The distance between the slits will remain the same. Fine. Yes, class. Now see, if they are overlapping, it means yn is equal to ym. This was from where you had to start. Otherwise, you won't be getting the values as 5 or 6. 5 or 6 you're getting consecutive, that is correct. But it is not 5 and 6 because you have to equate it and then start it. Did you equate it? Okay, fine. Now see, so yn is equal to, so both are bright fringes. So what we'll do, we'll write it as n lambda d by d. So let's write this as n lambda 1 d by small d and this as m lambda 2 capital D by small d. So capital D gets cancelled, small d gets cancelled. Now value of lambda 1 is given to you as 800 nanometer and second one is given to you as 600 nanometer. So n into 800 is first, no? So see here, this is n into 800. This is equal to m into 600. Nanometers will also get cancelled. So see, n by m ratio first let us take out. Now see, n will be equal to m into 6 by 8 you can write, and this you can write as 3 by 4. So n is equal to m into 3 by 4. Now see, you know these fringes cannot be in integral values like in decimals or in fractions. So m cannot be n value or m value. See, n's value depends upon m. So n's value cannot be 0.5, it cannot be 3 by 4, it cannot be 5 by 8 or any other values. These values are not possible for n. So we have to keep on checking. If we put value of m, here you have to do hit and trial method. If you put m as 1, you get n as 3 by 4. Fraction not allowed. M as 2, n as 2 into 3 by 4. You're getting 3 by 2, not allowed. M is equal to 3, n is equal to 3 into 3 by 4. 9 by 4, not acceptable. So once you put m as 4, you get 3 by 4 into 4. So 4 gets cancelled and this comes out to be 3. This n comes out to be 3. Once you have n is 3, next one m will be equal to 4, the next consecutive one. Understood here? M is 4, so n is 3. So it means the one where they overlap with each other are 4 and 3, not 5 and 6. Why not 5 and 6? Because initially you have to find the least distance where they are overlapping with each other. It's written in the question, calculate the least distance. That's why not 5 and 6. Clear? Note down the solution. Any doubts you have, ask me. see both the fringes are having some fringes number. Like n is having 3 fringe. So third fringe of the 800th wave matches or overlaps with the fourth fringe of the 800th one. Like this. This is the meaning of the answer. N as 3 and M as 4. So quickly write done in the chat box once you write it so that we can now start with diffraction. Apart from Samaira, all of you have completed? Okay. Now see, you have the last topic of this chapter, that is diffraction. So diffraction is not a very lengthy topic, but many things are similar to interference, but certain the point of differences are there. See what is meant by diffraction basically. Wherever, let's say I have taken a screen. Let's say here let me try it. Here I have taken a screen. And here I have taken some opaque block. This is totally opaque. Now light is passing. So when the light will pass through here, it will reach. When the light will pass through here, it will reach. When the light will pass through here, it will reach. All these lights will reach. But as soon as the light will hit the corner that is present, let me draw it a little. Now see, as soon as the light will be touching this corner part of it. So what should happen? It should just stop here because this is opaque. If this is an opaque wall, this should have stopped. But what will happen? When it will coincide here, you will see that the light is getting bent. Light rays, whatever amount of light rays that are falling here, they are getting bent. Otherwise, we all know light travels in a straight line. So this phenomena of bending of light of around any corner of any opaque object you have, any obstacle you have, any aperture you have, that is known as diffraction. This phenomena that is occurring here, this is known as diffraction. Now see, wherever there is light, you will be able to see light on the screen. Wherever these rays will not fall on the screen, that part you will be able to observe shadow. This is known as geometrical shadow. So what is the definition of diffraction? Phenomena of bending of light around the corners of small obstacles or apertures, and its consequent spreading into the regions of geometrical shadow is called diffraction of light. So phenomena of bending of light gets bent and it's spreading into the regions of geometrical shadow. This is known as diffraction of light. Now, diffraction is also not of single type. Diffractions are basically of two types. Fresnel's diffraction you have, if the separation between the source, slit, and screen is fine. It means this is the source, this is the slit, and here you have the screen. This is finite. Let's say this is 5 meters, this is 3 meters. You can calculate. Then that is known as Fresnel's diffraction. If it is infinite, source is somewhere at infinity distance, you're getting the slit, then at infinity distance, you're getting the screen. That type of diffraction is known as Fraunhofer's diffraction. And Fraunhofer's diffraction is a part of your syllabus. No need to go into the details of Fresnel's diffraction. Fraunhofer's diffraction are basically like wavefronts for distant sources. Best example is you can take the example of plane wavefronts. Note down the introductory part, then we'll actually start with diffraction for a single slit. Double slit, we have done Young's double slit experiment. Let us start with this diffraction at a slit. Note down these 2 points quickly. Now see, single slit diffraction is basically Fraunhofer's diffraction. I hope all of you have written. So let me first explain you the diagram. You can note down the diagram first and understand whatever points you have to study. And then let me know if you have any doubts and I'll tell you the derivation. Derivation part is not very difficult. Now, once you have understood interference, this is easier to study. Now see, we do not have any opaque object to get diffraction possible. So we'll take a lens. So source will be here located, but we'll take a lens so that this gets bent. Whatever sources the radiations are coming like this has to converge, not a point. So for that particular point, we are taking it. Now see, from here, let me draw it properly. Like this. Now see what will happen. All the light rays that will be coming will pass through it like this because the lens has only converged it. Now I'm just leaving some space for the slit to pass through. Let's say the slit is still here. This is the single slit. This is entire slit. Let's say slit width is small a. This is the slit. Now the rays are falling, and let's say here also, let me place a lens, a huge lens, so that it keeps it intact. Because we have to obtain points where more convergence will occur. Like this, supposedly at this point diffraction will occur. At this point diffraction will occur. See class, diffraction will occur at the edges. These edges refraction will occur. Name it something, let's say CD. So refraction will occur at this CD. So when it will occur, refraction will occur, something has to be there to converge it at any particular point. So that convergence that is occurring like this particular, that's why we had take the second lens. Let's say this angle is some theta n. This is some angle theta n. Here you will get the central maximum, central bright fringe. Instead of central bright fringe, you will be getting here the central maximum. See class, same construction, rest of the thing will remain the same, whatever you have studied. Understood? Now see, let's do one thing. Let's drop a triangle here. A perpendicular I am dropping, let's say this is n, Cn, fine? So this triangle becomes CDN. So in this triangle CDN, if you try to find out value of sine theta, this will be theta according to the geometric construction. So in triangle CDN, if you write down the value of sine theta, this will be, see here, it will be perpendicular, that is dn, divided by the hypotenuse, that is CD. So sine theta will be dn by CD. Now see, from here, one more thing class. Okay, dn will be equal to, sorry, CD will be equal to, if you look here, CD is equal to the, correct, A. Yes, right. This is equal to A, the slit width. So if it is equal to the slit width, so A will be equal to dn. dn will be equal to A sine theta. From here, dn will be equal to A sine theta. A sine theta. Fine. One more thing, class. One more thing. In the same triangle, if you write tan theta's value, tan theta, in, let's take a bigger triangle, take this triangle, make this point as P point where they are meeting, and take this point as some E point. So take this triangle, PDE, this big triangle, PED. In this triangle, what will happen? Or take this as E point. Don't even take this, a huge triangle will be formed then. Take this point as P. Now see, in P, and let's name this point as O. So POE, this huge triangle, what will be tan theta equal to? This will be the separation between the central maxima and the point that is formed at P, yn. So this will be equal to, and see, separation between the slit and the screen will remain capital D. So tan theta will be equal to yn divided by capital D. So from here you can write yn is equal to D tan theta n. Even if you use small angle approximation, your yn will be equal to D theta n. Now using this, we'll write down the rest of the conditions, note it down. From here, we'll be writing the rest of the conditions. First, make this figure. Now see the conditions for secondary maxima and minima. Now here whatever you will be getting in terms of bright fringes and dark fringes, you will not be naming it as bright fringe or dark fringe. You will call it as maxima or minima. And there you had there you had central bright fringe. Here you will be having central maxima. Now see n its secondary minima's condition will be, see n lambda was the condition for bright fringe. Same way here you will replace the path difference a sine theta by n lambda. Rest of the things will remain the same. From here also if you want you can write sine theta as n lambda by a. If you use small angle approximation, theta will almost be equal to n lambda by a. And this is what? This is the angular separation. Theta n is the angular separation. This formula, this is angular separation. Suppose, let's say, linear separation you have to calculate. Yes, I'll scroll up. Just let me write this part. So linear separation will be theta n capital D. Just now you all have written tan theta 1. So put the value of theta n. Theta n just now we had seen this is n lambda by a multiplied by small t. So this is linear separation. So there is a difference between linear separation and angular separation. Terms remain the same. See here class, terms remain as it is the same. Now for path difference for maxima, 2n plus 1 lambda by 2 will be used. Whatever you have used for minima and whatever you have used for bright fringe, that will be applicable for minima. And for dark fringes, maxima. And in terms of central bright fringe, you will be using the term central maxima. Rest of the things are the same. Now here, 2n plus 1 lambda by 2 is the path difference. So a sine theta will be equal to 2n plus 1 lambda by 2. Sine theta will be equal to 2n plus 1 lambda by 2a. And theta will be equal to 2n plus 1 lambda by 2a. So this is the angular separation. So linear separation will be theta n multiplied by lambda d by a. So theta n was 2n plus 1 by 2a, just multiplied by lambda, just multiplied by capital D. This is the linear separation. So these are all the conditions of maxima and minima. So maximum part of diffraction is this only. Let us practice one or two questions. Do one thing, note this down first, then we'll practice two numericals. Yes, Fahad, till here, I hope it's fine. Or what you want me to scroll up more? Okay. Now, C class, one question, let's practice. Two questions at least we'll practice. It says that a parallel beam of light of 600 nanometer falls on a narrow slit and resulting diffraction pattern is observed on screen 1.2 meters away. So wavelength is 600 nanometers. Separation between the screen and the slit is 1.2. So 1.2 meters is what? Small d or capital D? Yes, class. Separation between screen and slit. Good, Fahad. Capital D. Separation between screen and slit is capital D. Why am I saying this? Because be particular about it. Otherwise, you will be getting confused whether it was small d or capital D. Because in the formula, you have both the D's. And separation, it is observed that first minimum is first minimum is at a distance of 3 millimeter from center of screen. Calculate width, whatever is the width given. So bright or dark, first minima we have, no. So for minima, formula is already n lambda t by a, right? The formula that you have just calculated, the value of yn is what? N lambda d by a. N is given to you, yes, first minimum. So see, Fahad, like this only, first minimum is mentioned. So this will be it. So N is 1. Lambda is 600 nanometer. That is 600 into 10 to the power minus 9 meters. Lambda. Okay. Capital D is 1.2 meters and width, distance of 3 millimeters, means both are separation at a separation of 3 millimeters. So small d, here we have a, that is 3 into 10 to the power minus 3 meters. Just we have to keep everything in the form. So questions from diffraction and interference, no numericals, these are like this only. Main formula you have to remember. Values just you have to check. So y1 will be 600 into 10 to the power minus 9 into 1.2 by 3 into 10 to the power minus 3. So 2.4 something, no? This is, yes, it will be around 2.4 something. Just check whatever answer you're getting, that will be the final answer. So quickly note it down, then one more numerical we'll see. 2.4 into 10 to the power minus 4. Okay. See, this says that in single slit experiment, light of wavelength 6000 angstrom is used. Slit width is given to you 2 millimeter and separation of slit from screen is 2 meters. Now you have to calculate separation of first secondary minima from central minima. Central maximum, angular and linear both, and separation of second secondary maximum. So let's do only the first part. Second part is just exactly the similar to the first part. See here. Capital D is given to you 2 meter. Separation between both the slits 2 millimeter and wavelength 6000 angstrom. So if you calculate theta n, that is n lambda by a. N is, we have to calculate first one, wavelength is 6000 angstrom. So 6 into 10 to the power minus 7, and a will be 2 millimeters. So 2 into 10 to the power minus 3. So you will get 3 into 10 to the power minus 4 radian, angular one. This is the value of theta 1. Same thing if you have to find it for y1. Instead of multiplying the entire thing and writing it, just multiply theta n by d. So theta n is 3 into 10 to the power minus 4. Capital D is 2. So that is 6 into 10 to the power minus 4 meters. Same way, if you want to calculate for the second part difference will just be in the formula 2n plus 1 lambda 2a. Formula based class. All the questions are formula based. That's why I'm not even doing so many questions. Just like this, all the questions are. Note it down. Then now intensity distribution curve for this also diffraction I'll show you. And almost we are towards the end of this topic. Yes, they will mention. They'll mention it to you. Angular or linear. That will be clearly mentioned. Okay, before that, one more thing. Width of the central maxima. If the central maxima, again, same thing, angle that the central maxima is subtending. So if this is theta 1, so total angle that it will be subtending will be 2 theta 1. And theta for first, we have calculated lambda by a. So total angular fringe, total angular width of central maxima will be 2 lambda by a. And now see, if you have to find out the linear width of it, how much is the linear separation? That will be simply whatever is angular width multiplied by the distance. So angular, it's like length of arc multiplied by the radius. It's like this only. So you will get linear width as 2 lambda by a is there multiplied by this d. This can, numerical from this can be asked. It can be asked, formula based, it can be asked. Usually width, this topic, no, we are just towards the end only. Intensity distribution one we have to see, and then it will be over. Done. See, for the intensity distribution curve, no, we'll see values for each. Like for path difference, that is n lambda. So first minima will be 1 lambda. Second minima will be 2 lambda. So third minima will be 3 lambda. And like this, it will keep on moving. For maxima path difference, this will be n's value will be different. So it will be 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, and all the odd values. Now, see, if you plot the graph, you will notice that intensity will be decreasing. Here, you will notice that intensity is decreasing. Whereas in the graph, you observed that intensity was constant and independent for non-coherent. So like this intensity will keep on decreasing. Now, why have I written I by 21? Why have I written I by 61? That is totally derived through certain derivations. That is not a part of your syllabus. You just remember, if by chance you are asked to draw the intensity distribution curve, do write these values. But how it has come exactly, that is done by certain derivations which are not part of your syllabus. You just have to remember intensity is decreasing. So if you make a comparison between interference and diffraction. So see, superposition of light waves from two coherent sources is interference, and diffraction is superposition of secondary wavelets from the same wavefront. Fine. Then this is bright fringes have same intensity in case of interference, and here you can notice the intensity is decreasing. Third one, all the fringes have the same width, while the fringes can have different width. And last one is that there's a good contrast between the bright and the dark fringes in interference. But there's a poor contrast between the minima and maxima. Here you won't use bright and dark fringe. So that was all about diffraction. Note down these points wherever you are having difficulties. Let me know. Keep on texting me done once you have completed. So then I'll stop the class. Yes, those values you have to remember. That's what I was saying. When you plot it, just to mention one or two values. yes, that is minus 5 lambda by 2, not 3. I'll correct it. Yes, right, Fahad. Okay, class, you can leave. This completes with wave optics. Diffraction is also over. Any doubts you have, please let me know. Now we are left with modern physics and semiconductors. So half or the maximum portion of modern physics we'll be completing in the next week. Thank you so much. Any doubts if you have, you can let me know. Otherwise, I'm ending the class. Okay, thank you so much.